Good afternoon. Today I'd like to give a presentation about 3D image acquisition and processing. This is the 3D image communication system. First, a scene, 3D scene, is captured by some 3D cameras, and then the data is compressed, coded, transmitted, and then at the receiver side, 3D display displays the 3D scene as today's topic is divided into 5 parts. The first, I'd like to define what is a three-dimensional image. And then the second is what is ray space or light field theory. And next, the ray space acquisition system and coding of ray space and the total system. So let's start with what is three-dimensional image. So I'd like to show you this slide first. Okay, the left side is 2D image, the two-dimensional image. The right side is 3D image. It is called 3D image. But is this real 3D image? It's just 2D image. Okay, left eye and right eye, we call it 3D image, but it is not three-dimensional. Two-dimensional images. So that arises a question: what is a 3D image? Is the dimensional 3? So we have to consider, in this case, human factor. How human feel 3D feelings. Okay, so the first, these are the human factors of stereoscopic effect. So the first is size. Okay, the left side, the front object can be seen the bigger than the rear object. This is size. The perspective, it is often used by painting, the perspective. And overlapping, the second one. And third one is shadow. So it is very interesting. This figure and this figure is just the same, but just 180-degree rotation. But you can see convex sphere or concave sphere. Seems different, but the reality is the same. This is very interesting phenomenon. The shadow and the texture, we can feel three-dimensional feeling. But these are not called three-dimensional image. These factors are used in 2D image. So what is three-dimensional image? There are 4 factors which a three-dimensional display can provide. Okay, first is disparity. Disparity means this one. In Japanese, this ryogan shisa. Disparity. It is a difference between the left image eye and the left eye image and right eye image. This is a disparity. The second one is convergence. Convergence means the rotation of eyeball. And the third is accommodation. Accommodation is the adjust of the focal length of eyeball. Accommodation. And the motion parallax. Okay, these 4 factors: disparity, convergence, accommodation, and the motion parallax. So 3D displays, we call, utilize these factors. These are very important. These 4 factors are essential factors that 3D displays can provide. Okay, please remember these 4. Okay. So now I'd like to go into the detail of the 3D displays, and we can now we can see many kinds of 3D displays in the market. So what is the original of 3D image, a 3D display? Do you know that? This is the very first one, the 1838. This is called Wheatstone stereoscopic image. Left eye sees left pictures, right eye sees right picture, and we can feel stereoscopic effect. This is the very first 3D display, 1838. Okay. And the next is the beginning of 20th century, 1903. Ives invented parallax stereogram. Parallax stereogram composed of the left eye image and right eye image composition of this image, this side. And the barrier is placed here, and the right eye sees only this part, or this part, this part, this part. And left eye only sees this part, this part. So, in short, left eye image and right eye image are separated using this barrier and slit. This is a very simple principle, but 1903, Ives invented this kind of 3D display. This is the very first one. And 5 years later, the Lippmann invented integral photography. So this technique uses lenslet. These are very small lens, convex lenses, and the object is captured by this, like here. So this one lenslet is like a camera. So we can see many cameras are placed here. So we can see that. So this kind of technique is called integral photography. Okay, please remember this word. Okay, I review this. One is barrier and slit, parallax stereogram, barrier type display. The second is lens type display, integral photography. Please remember these two. Okay. So these are very old technique, but very recent 3D display still uses this kind of technology, integral photography and slit type display. So please remember these two. Okay, now nowadays we can see many kinds of 3D displays, but these are categorized like this: binocular stereo, multi-view stereo, waveform reconstruction, volume scanning, and others. The first binocular stereo, it's very common. You can see everywhere. You put on glasses, or without glasses, this is lenticular type and parallax barrier, as I mentioned before. Just two kinds of very old technique. But if we put on the glasses, we can see left eye image, right eye image, and the 3D image. Okay, this is one. This is the lenticular type display. Left eye and right eye image are separated by lens. So remember, this is very similar to integral photography, but not vertical parallax is realized. Okay, so this is lenticular. So this is very recent, about 10 years ago. You can see a 3D type game, portable game, 3DS by Nintendo, uses this technique. But the principle is very old one, parallax barrier. Okay, and the multi-view stereo is also realized using lenticular lens or integral photography. And this is about 2000. Professor Takaki of Tokyo University of Agriculture and Technology invented this kind of very interesting 3D display. So he used very high number of projectors. In this case, 128 projectors are used. And 128 projector project 128 images on one screen, and we can see 128 view images, 128 view images. This is called high density directional display. The other techniques use this principle of holography. The holography is emerged not so old, about 1960s, when the laser was invented. So laser is coherent light. The coherent light can interfere, and we can see interfere fringe pattern. And the fringe pattern is recorded on the plate. So this is the other type of 3D display. And this is called ultimate 3D display because it's not just provides a left and the right image, but it reconstructs the waveform. So we cannot distinguish this image and real image. So as I mentioned, we have 4 factors for perceiving 3D, disparity and binocular, stereo, and convergence and accommodation, the motion parallax. All 4 factors are fulfilled by this reconstruction of waveform. This is called the ultimate 3D display. But as you can see, this is still image, not a video. So about 1919, Professor Benton of MIT invented this kind of holography video. This is very interesting technique. And fringe pattern is fed here, but optical SLM, spatial light modulator. Fringe pattern is fed this. The hologram signal is fed this. And the laser is emitted from here. And then laser is modulated by this SLM. And then we can see a reconstructed image. This kind of electrical holography is now still researched by many researchers. The holo video is the very first holographic video. And this is integral photography. This is invented in 1908, but NHK, Nihon Hoso Kyokai, in the broadcasting company, is they reinvented integral photography by recent technology. So they have very high density display panels or camera. So they used this for 3D image capturing and display. So object is captured by lens array. The lens array image is like this, and the viewer can see 3D image. The principle is just completely the same with 1908 integral photography. But now they still continue 3D image based on integral photography. This figure is from NHK's leaflet. So they are using integral photography. So the image is like this. That you can see a left viewpoint image from this, from left side like this, and right image, upper image, and lower image. So as you can see, resolution is not so high, but the resolution is just the same with the number of lenses. So number of lenses is not so high, so the resolution is not so high, but the direction is about 20 by 20. So you can see about 400 images from different directions. This is their technique. And other is depth-fused 3D image. This is invented by Professor Suyama of Tokushima University, but he worked for NTT in about 2000. So their group invented this kind of technique, depth fused. So they used just two layers. So the front layer displays this kind of image, and the rear layer displays this kind of image. So if the subject see these two layers, so subject perceive this object is near the subject, and this object is far from the object. So this is they call this is illusion. So this is not fully investigated, but this phenomenon occurs. So they use this phenomena as a 3D display. So this is very interesting. So some company produced this kind of volume display. That is a very old technique. Or 3D light source can be displayed on real 3D using plasma technique. This is invented by Sansoken. Yes. And this is another very interesting 3D display. This is cylindrical 3D display. So first I can show you video. So please see this one. So you can see as if a person is inside the cylinder, but it's just an image. So Professor Endo, he worked for Nagoya University with me, and he constructed this 3D image. So it's a very interesting one. But the principle is, as I said, very old. Just barrier and slit, using slit type parallax barrier. But he introduced some moving parts, rotating parts, and increased resolution and increased color. So, and he improved from very beginning of parallax barrier image, but so very sophisticated techniques. And other technique invented by NICT. NICT developed this kind of cube, but this is based on integral photography again. So this is called F-Vision. Dr. Yoshida invented this one. So it's tabletop 3D display. This is the real object, but this is just image. But you can see a pop-up image here. This is F-Vision. And this is 200-inch 3D display, very big one. So they used 200 projectors. 200 projectors and the lens, very large Fresnel lens and the lenticular lens, and displayed 200 view images. So this is very impressive. And this was exhibited in the Osaka station. So now it's disappeared because of budget, but a very interesting one. Okay, now I move on to the second part, rate space and light field theory. So now we have seen the many kinds of 3D displays. So this is a very old discussion when I was a student, a PhD student, 1992. So, and Professor Harashima was my advisor, and we are discussing the future of 3D communication. So at that time, there were many kinds of 3D display emerging, and so in the future, we discussed in the future, possibly many kinds of 3D displays become common, but how do we construct a 3D communication system? There are many kinds of input devices, and there are many kinds of output devices. So how can we connect this one? So very simple one is this. The multi-view image capturing system sends the image and displays multi-view image. The computer-generated image is displayed by spatial imaging, and the holographic fringe pattern is transmitted and then reproduced by holographic technique. But this is not efficient. So we discussed this kind of new common data formats can be defined and then this very total system can be constructed. So there were very old discussion. The many kinds of input data is converted to a common data format, and then at the receiver side, it is converted to many types of 3D display. So the next question is, what is this common data format? So this figure is from my PhD thesis, 1994. So many kinds of 3D image is converted to just one common data format. And then it's compressed, processed, and transmitted. And then at the receiver side, the common data format is reconverted to many kinds of 3D displays. This is a very old discussion. So again, what is a common data format? So from this discussion, we derived this ray space representation. Okay, so this is 3D scene. The object is here. And in the old sense, 3D image is just left eye image and right eye image. Or in multi-view case, many this image, for example, 128 view. This is 3D image in the old sense. So, but we redefined this concept by using ray. So this is 3D scene, and this is object. So we define this reference plane. In this case, z equal to 0. This is plane. And the light source emits light, and the object reflects this light ray. And the light ray comes here and intersects with this reference plane at this intersection point, xy. And emitting direction is, for example, theta and phi. So we can specify one light ray using 4 parameters: intersection points xy and direction theta and phi. So we can define a 4D space function. Okay, this is intensity f, light ray intensity f can be determined using 4 parameters: x, y, theta, phi. So we can define a 4-dimensional function in this case. So this is called ray space. Okay. So this is very basic characteristics of ray space. The left is real space, top view. So light ray comes here, and the intersection point is x, and the direction is theta, the 2-dimensional case. And in the ray space, x and theta, but theta is transformed by tangent. So u equal to tangent theta is used in the vertical axis. The x and u. Okay. So one light ray, in this case x and theta, is mapped to one point, x and theta. Okay, this is x and theta plane. So this one light ray, x theta, can be mapped one point in ray space. So consider a bunch of light rays which traverses here, which goes through this point P, xz. These many light rays is mapped to a line of ray space. Okay, this is very basic and important characteristics between real space and ray space. Please remember this. So, what is the benefit of this presentation? So, let's consider that we capture this 3D scene using 5 cameras, for example. Okay. So, let's focus on this number 3, camera number 3. So camera number 3 captures these scenes, but what information does this camera capture? So, what is the relationship between this and ray space? So, 3D in 3D scene, there are many light rays emitting, and camera 3 captures only light rays which traverses the lens of this camera 3. So, let's go back to this. Okay, let's consider this point is camera 3, for example. So, the camera 3 captures many light rays which traverses this point P. And based on the relationship, ray space, in the ray space, these light rays align on the line. So this relationship can be converted like this. This camera 3 captures the line image in ray space in XY, XU. And if we pile up in Y direction, we can get the 3D function XYU. So camera 3 image is the intersection of the red line and the box. Okay, this is the basic characteristics. So once we get full ray space, just cut this box. For example, this red line cross-section corresponds to cross-section image 1. And this blue section image corresponds to this. So this ray space includes whole information of 3D scene. So just extract one cross-section, we can get free viewpoint image. So this is derived from the characteristics of real space and ray space. So this is very basic principle. Okay, so this is the main point of ray space theory. So what can we do? For example, we can generate stereo or a merge view image that we can create a refocused image in this case. So as you may know, Lightro produced this kind of light field camera on in about 2005 or 2006. They are not a Stanford University group. So they used this light field or ray space theory to this camera. And this is a refocus image. I'll skip this. Okay. So to conclude, we can get ray space from this real space. The ray space is like this, and we cut ray space, we can get free viewpoint images. This is a point. Okay, so I'll skip this. And now, this is the answer. Ray space or light field is the common data format of 3D image communication. So data acquisition part captures 3D scene or light rays. And the ray space is processed or coded or transmitted to the receiver. And the ray space, from ray space, we can extract any viewpoint image and then displays to any 3D displays. So this is the center concept of the ray space. Okay, so now it's 10 minutes. So first, we focus on data acquisition. How can we acquire or obtain this kind of light ray? So there are roughly 3 techniques. Multi-camera system, like this. So we use many cameras. This is 8 cameras, 4x4 cameras. And we constructed this kind of 16-camera system. And about 2005, Bennett Wilburn, he was maybe PhD student of Stanford University at that time. He constructed 128 camera image. Or Carnegie Mellon University developed this kind of multi-camera system. And we, Nagoya University, developed 100 camera system. In 2002 and 2007, this kind of multi-camera system, this is 100 cameras, 5 centimeter spacing, 100 cameras. 20 cameras, 5 rows, 100 camera. So this is ICME paper, and Mori sensei is here. He was the speaker. Mori sensei was here. And Takeda sensei also here. Okay. And the specification is like this. Resolution is not so high, 3092 and 1040, but the raw data, non-compression, this is very important. And the camera is like this, and 100 cameras, and 100 cameras in 1D arc, 100 cameras in 2D arrays, 20 cameras by 5 rows. And we captured many scenes using this 100 camera system. So this is one example. So this is like a movie, a Matrix, but we captured this in 2004 or 2005 using 100 camera system. And we used this camera system as a traffic accident monitoring. This is collaborative work with Takeda sensei. He captured sound also. Okay. Okay. But there was a mess. many cables. So yeah, it was very hard work, and to align the camera is a very hard work using post-it here. So this camera calibration is very hard work. So we used post-it. It is called post-it calibration. And we so this is too heavy. So we developed other kind of capturing system. This is camera, and this is a PC, very small PC, Windows XP PC. So very interesting one. So this kind of system, and we capture. This is like this. So 16 camera system. This is one. Or we captured sports scene like this. This is beach valley, and high-speed camera is also equipped, so we can capture this kind of slow motion effect. This is 16 camera system, and we captured soccer scene using 16 cameras. This is Teikyo Koko. And we captured figure skating. This is Arakawa Shizuka-san, the gold medalist of Olympic. Okay, this is multi-camera system. And the second one is space division multiplexing. Space division multiplexing, okay, this is appears again. This is integral photography. This is space division multiplexing. Okay, and time division. This is very interesting. Instead of using 100 camera system, this is very heavy. We use just one camera, but this is moving, and the time multiplexing system. So we constructed some optics like this, and the object is pig here. The on the bottom of a parabolic mirror. And we use this and developed some board. And this is real image of the object, the peak. And the galvanometer mirror oscillates. And we capture this image using high-speed camera. I'd like to show you this demo like this. So we can see multi-view images just moving galvanometer mirror. For demonstration, this is very slow, but actually this oscillates 50 frames per second. So it's like this. So remember the ray space. Though this is like the ray space scanning. Okay. So this camera, this new types of camera captures real ray space 3D scene and extract just one view, okay, from ray space. So this captures the whole ray space and processed and then cut and extract the cross-section image, and we can see a multi-view image like this. So this is just half of a circle. So we constructed 316 degrees system. So as you remember, this is cylindrical 360 degree 3D display and 360 degree ray space camera. Okay. The camera is directly connected to 3D display. So I can show you demo. So this is again pig here. And this is 360 types ray space camera and real-time display on 3D cylindrical display. So we developed this kind of system. So bandwidth is very high, maybe 5 gigabit per second. It's very high. Okay, so let's conclude that this is the total system. So let's jump to total system. Okay, just this is last part. Takes 3 minutes. So free viewpoint TV system. So we developed this kind of system. This very small black part is camera. So we captured 16 views from the many directions and generate free viewpoint image. And again, this is a 16 camera system. The object is aquarium. We used aquarium scene. So whole system is like this: video capture, and some correction is done, and encode, decode, and view generation and display. So this is input system, input image, the 16 views, and we construct ray space, or light field, and then the extract scene. So this is generated one. After ray space processing, we can see this kind of free viewpoint image. So interesting thing, we can go through the aquarium. This is very interesting. This is not enlarging, just enlarging, but we can really go into the aquarium. Okay, this is the total system. Okay, first, okay, let's conclude. This is the beginning of my presentation. Scene is captured by 3D camera, and just 2 images are transmitted and 3D display. But should be like this. There are many kinds of capturing system. And the common data format is ray space or light field. And it's converted to many kinds of 3D displays. So this is from IEEE Signal Processing Magazine in 2007. So multi-view imaging was 3D TV, and he is watching race space there. Yeah, this is one. Okay, thank you very much. Any questions? Any questions? Yes?
I think this 3D one is more horizontal 3D. I think 3D is also vertical. Is there vertical 3D?
Yes, of course. There are, as you said, two types of 3D displays: a horizontal only parallax type and full parallax type. And integral photography is full parallax type. And other type, for example, lenticular or some other, for example, cylindrical 360 is just horizontal. So, of course, it can be extended, but data bandwidths or some optics are very difficult to construct. So, maybe in the future, it should be full parallax. But integral photography is, at this stage, already full parallax. Any other questions? That you understand completely? Okay, thank you very much.